So now we're going to look at what happens at the equivalence point of a weak acid strong base titration. And remember, we've already said that we understand that the pH is going to be greater than 7. And so we now need to take a second and understand why is the pH going to be greater than 7. And I'm not going to sugarcoat this calculation that we're going to do for the equivalence point of a weak acid strong base is probably one of the more complex calculations that we do in general chemistry. So if you notice that you're at the equivalence point, you need to pay attention because there's going to be multiple steps and there's a lot of places to get things wrong. So you need to be very, very careful during this. So the first thing we want to do is prove to ourselves we are at the equivalence point. So as always, I see that I'm starting with a weak acid and I'm adding a strong base to it. I understand that that means we're going to be doing a neutralization. Because of that, I want to find out how many moles of weak acid I started with and how many moles of hydroxide I've just added. So moles is equal to molarity times volume. The molarity of weak acid was given, the volume was given, and we know that we started with 0.50 times 10 to the minus third mole of our weak acid. I then find out how many moles of hydroxide that I've added. That's molarity times volume also. So I have added 5.0 times 10 to the minus third moles of our strong base or hydroxide. So you can see that because the number of moles of weak acid that we started with is equal to the number of moles of base, we are at the equivalence point. So that's the true that when the moles of our acid are equal to the number of moles of base that we've added, we are at the equivalence point. So we've completely neutralized, in a sense, the amount of weak acid that we have. So if we look and we do the subtraction like we've been doing during this titration curve, if I started with this many moles of weak acid and I have this many moles of hydroxide that I've added, normally the hydroxide uses up the weak acid. That's saying that I have 0 moles of hydroxide left, and that's going to be a problem. So we'll talk about that in a second, but what we've really done is we've converted all of our weak acid into the conjugate base. So we have 0 moles of our weak acid left, but then we remember we're making conjugate base, and the amount of conjugate base that we make is equal to the number of moles of hydroxide added. We know how many moles of hydroxide that we've added. We calculated that here. So this tells me how many moles of our conjugate base are made. So in this situation at the equivalence point, we have completely used up all of our weak acid and we converted all of it to our conjugate base. So now the pH is going to be determined by the Kb reaction for this conjugate base. So we've talked about that before. The conjugate base of a weak acid is basic. And so in this case, acetate or Ac minus is our conjugate base. This has a whole Kb reaction that produces hydroxide. And in this case, we'll look at that in just a second. So this is back to a basic equilibrium problem. So because we're at the equivalence point, we're not going to be using the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is only in between the starting point and the equivalence point. So anywhere in between there, we use the Henderson-Hasselbalch equation. So here we're at the equivalence point, so we are not going to be using that. So it goes back to finding concentrations and looking at equilibrium. So really what I need to find now is what's the concentration of acetate that we had. So we just figured out how many moles of acetate we have. Now I got to find out what the concentration is. So I need to know what the total volume is. And I got to realize I started with 50 milliliters of our acetic acid solution, and during this titration I've added 50 milliliters from sodium hydroxide. So if you remember, we go up here, I started with 50 milliliters of acetic acid and I've added 50 milliliters of our sodium hydroxide. So this is a very, very common mistake that people make, is they forget that the total volume is equal to the summation of these two. A lot of times they'll just say, oh, well, we have so many milliliters of weak acid, and they'll use that as the total volume. So during titrations, actually there's a dilution going on because we are adding in solution of our strong base. So the total volume is equal to the addition. How many milliliters of weak acid we started with, plus the number of milliliters of strong base that we have added. So because we had 50 milliliters of each of these, my total volume is equal to 100 milliliters. Now I want to find the concentration of my conjugate base. That's moles. Okay, we found that right here, divided by the total volume in liters. So the moles we have, the volume, 100 milliliters or 0.1 liters. I get my new concentration of acetate, 0.050 moles. So the other thing we need to realize is we're going to be looking at a Kb reaction. And in the original problem up here, I've given you the Ka. We don't want the Ka anymore because the weak acid's been used up. What we have left is our conjugate base, acetate. And we understand acetate is going to undergo a Kb type reaction, and that Kb reaction is going to be what's determining my pH. So I need to know what Kb is. So we're going to utilize the fact that Ka times Kb is equal to Kw, or Kb is equal to Kw divided by Ka. Kw is a constant. It's for the self-ionization of water. That's 1 times 10 to the minus 14th. Ka was given, so I can calculate Kb. So Kb, the one that we're interested, this is going to be the reaction that is determining the pH now. Kb is equal to 5.6 times 10 to the minus 10th. So it's this Kb reaction. So what do we mean by that? That this conjugate base has a Kb reaction. It can react with water to reform our weak acid and to form hydroxide. So remember, that's what tells us that we're dealing with a Kb reaction, is that hydroxide is produced as one of my products. So we want to find out now how much hydroxide is left. So this is very much like the starting point, but now we've kind of flipped things around. We're saying we're looking at a Kb, and now we want to find out how much hydroxide is being made. So we understand that we have 0.05 molar acetate, and that in the original titration, remember we said, oh, well, we've added in an equal amount of strong base and weak acid, therefore we have 0 moles of our weak acid left. That can't be true, because our weak acid, acetic acid, is part of an equilibrium, so you really can't have a 0 concentration of this species. So what happens is some of the acetate is going to dissociate to make some of this weak acid. So we can't have a 0 concentration of acetic acid. Some of this is going to dissociate to make our weak acid, acetic acid, and in doing that, that's going to create a little bit of hydroxide, and it's this hydroxide, this X, is what's going to determine the pH of our solution. So we say we start with 0.05 molar of our acetate. Some of that dissociates X to make X amount of acetic acid and X amount of hydroxide. We then say the Kb expression, products divided by reactants. Remember, water doesn't make it into it. And we plug in our algebraic expressions into the equilibrium expression down here. So the same deal, we assume X is small, so this goes away. And we combine these two X's to make X squared, and then we solve for X. When we're done with that, we get an X value of 5.3 times 10 to the minus 6 molar. And this tells us, this equilibrium expression up here tells us that X is equal to our concentration of hydroxide. So when we solve from X in this case, that's telling us our concentration of hydroxide. So remember, we want pH, so we don't want, a POH from this. So we want to get to the pH. So the easiest way of getting to that is to find the POH first. Here we have the concentration of hydroxide. We're going to find the POH, which means the negative log of the concentration of hydroxide. We plug those values in, we get the POH of being 5.3. We then realize that pH plus POH is equal to 14, or pH, or 14 minus the POH gives us our pH. So in this case, the pH is 8.7. So this is why the pH at the equivalence point of a weak acid strong base titration is greater than 7, because we have converted our weak acid into its conjugate base. The conjugate base has a Kb reaction, and in doing that, it creates a little bit of hydroxide, so the pH is going to be greater than 7.